Hello, welcome to more lectures on astronomy. This lecture we're going to be talking about comets and asteroids, and that's from chapter 13, and then we're going to jump to a bit of chapter 14, which we already looked at a bit when I was telling you about the formation of the solar system. So this is other parts of that chapter we didn't really talk about then, which is about meteors and meteorites. Broadly speaking, things that aren't planets, moons, rings, other than the main sort of stuff we talked about, most of the other stuff in the solar system are what we term asteroids or comets. Just some examples of some asteroids on the left there. Ida, or Ida, I'm not really sure. Vesta. Vesta is one of the largest asteroids we know of. You can see like Ida is pretty misshapen. It's not a particularly large asteroid, so its own gravitational pull on itself doesn't seem to have like formed into a sphere. Once you get to large enough objects that the gravitational pull tends to want things to come into like this spherical shape. So Vesta is pretty darn large, so hence pretty spherical. Over here we have Comet Neowise, I'm not sure how to say it. But this is a fairly recent comet, 2020, you might have seen it, or seen pictures of it when it was around that time. These things are sort of like the fossils of the solar system. And one very powerful way of investigating the early solar system is to investigate objects like this. Because, for the most part, they have not really changed much since the beginning of the solar system. They've kind of just been hanging out, roaming around the solar system, but they're not geologically active. There's not chemical processes going on for a lot of them, a lot of the time. So, yeah, for the most part, they've been stuck in like a sort of solar deep freeze since the beginning. So they kind of just preserve all the properties of the early solar system. So I'm trying to keep in mind sort of where things are in the solar system. When we talk about asteroids, well, there's this thing called an asteroid belt, which I've told you about before, and it's in that sort of break between Mars and Jupiter in the solar system. The name asteroid belt means there's a bunch of asteroids. So like ring almost of asteroids around the sun. There are also asteroids in sort of the further reaches of the solar system, but when you get kind of very far out, like past Neptune, a lot of those objects are not necessarily asteroids, which are more like rocky, and they're more like ices, which are generally more like comets. And just to note that you might have seen depictions of an asteroid belt in film. The asteroid belts, there's a lot of asteroids, but there's a whole bunch of room in the belt. So the asteroids are not really that close together. On average, they're like millions of kilometers away from each other, which is many Earth flights apart. And so if you're moving through an asteroid belt, you don't necessarily have to dodge the asteroids. There's a lot of room. So first we'll talk a bit about asteroids, and then we'll talk a bit about comets. Just to say here though, comets are generally in sort of the far reaches of the solar system. Okay? Outside of Neptune, and a lot in the Kuiper belt. There's also comets that have very odd orbits, very large orbits. But just keep it in mind, it's our solar system, and we got that asteroid belt, we got the Kuiper belt. And I think maybe we'll say very briefly something about the Oort cloud. It's sort of just like a spherical shell of dust and like ice maybe around the outside of the solar system. I'm really not quite sure. It's still technically like a theoretical thing. So some stuff about asteroids. Up here is a table of just some of the largest asteroids. Asteroids and comets, are not very large things. Like the largest one is less than 1,000 kilometers across. Even some of the largest ones mostly are a couple hundred kilometers across. And there's plenty of asteroids that are less than 100 kilometers, even like 10 kilometers or 1 kilometer, a little less than a mile or so, which might seem kind of big if you think about like a rock. It's like a mile across. But in terms of like trying to see those things and our ability to actually spot them when they're out in the asteroid belt or even further out, the Kuiper belt, it's very difficult. So we've cataloged a bunch of these asteroids, but there's almost certainly many, many more that we don't actually know of, or we haven't spotted yet, cataloged yet. However, it does seem that there's some like million, at least, asteroids in our solar system. The largest ones, there's only two that are larger than that, 500 kilometers. So up here, Ceres and Pallas? I'm not sure how to say that. Of the ones that are greater than 250 kilometers, about 15 of them, most of the rest of them there. To give you maybe a scale, Ceres, if it was on Earth, it would probably stretch, it's like roughly between like Napa, where I am now, and Portland, Oregon. So pretty large. But that's the largest of them. A lot of them are much smaller. Most of them are much smaller. One of the things in astronomy that's a little bit frustrating is the terminology and the names that are used for things are often dated in a way, and even though our understanding of objects and like ways of classifying objects maybe has changed, we still tend to use a lot of the old terminology. Yeah, something like Ceres probably would more classify as what we now call a dwarf planet, but we still tend to call it an asteroid. So deal with that. Some other things about them: most of these asteroids are orbiting around the sun in the same direction that the planets are, and there are small asteroids that regularly pass by Earth, and I think I'll mention later, but there was a project, at least by NASA, to catalog at least 90% of asteroids that came near Earth objects as they called them, and there were a lot of them. Yeah, I think this is actually something similar to that cataloging. Maybe it was a different project, I guess, attempting to find these potentially hazardous asteroids, ones that come within about 5 million miles of the Earth. So not that close, like in our perspective, it's still pretty far away, but planetarily speaking, it's pretty close. And in the depiction, I mean, it seems like they're everywhere, but the thing with trying to draw the solar system and things in the solar system is, as I tried to point out, it's very hard to draw it to scale, right? Any of those lines that's representing the orbit, the thickness of that line is far greater than the size of any of those asteroids. So in order to see the lines, you have to draw them a certain width, but in order to draw the solar system to scale, those lines would be basically invisible. You couldn't even see them. The darkest circle is Earth's orbit, and then Mars is outside of that, and then a big gap to Jupiter outside of that. And then the last column in there is compositional class. So we categorize asteroids in these different ways. This is C class, that's S, M, and yeah, let's talk a little bit about that. So these are the types or classifications of asteroids. There's sort of three main ones. C type is for like carbonaceous. This is because they have a lot of carbon compounds, which makes them dark, meaning they don't reflect a lot of light. So the C types seem to be the most common, make up about 3/4 or 75% of the asteroids that we see. These kinds of asteroids appear to be what we call like a primitive body, and primitive is a term essentially meaning that it doesn't seem to have changed much since the beginning of the solar system. Right? So since things started forming in our solar system, these bodies, primitive bodies, like not much has happened to them. They've kind of just been stuck in a deep freeze. C-type is mostly rock, but they have a lot of these carbon compounds, which makes them rather dark. So that's C-type. S-type, S for stony, also rock silicates, but they don't really have much of those dark carbon compounds. And then finally M, metallic type. Metallic because they're very high in metal. They have a high metal content, and they may be almost entirely made up of metals. These are rather rare, and these ones are difficult to study because, as I pointed out before, and as we'll come back around to more when we talk about stars, one of the key ways, one of the major ways that we study objects in astronomy is through spectroscopy, right? So we look at the light that is emitted from them. So most objects will either absorb light and re-emit it, or they might be generating their own light, like a star. And so by looking at that light, doing that stuff with spectroscopy we talked about a while ago, you can tell stuff about what it's made of and its temperature, things like that. However, for metallic objects, well, they're not heated, they're not emitting their own light, they're not generating their own light, and also metals tend to just reflect a lot of light, right? They don't really absorb it and then re-emit it. So this can make them difficult to study, but also being metallic, instead of trying to see the light that it emits, you can actually use a different part of the electromagnetic spectrum, like we use with radar, that we use on Earth. It just like bounces electromagnetic waves, radar waves off of objects like planes, boats, right? And those are metals. Radar works very well to bounce off of metals and come back and you get an image or an idea of the shape of that object. So then by sending radar waves out towards these asteroid belts and seeing some reflection, some bounces back, kind of get an idea that there are some of these out there, and you can maybe hone in a little bit on them and actually get a bit more information. The last type here, the book mentions, doesn't really specify much about it. I'm not exactly sure myself what to call it, but they seem to be very rare things in the world of asteroids, sort of oddities, and they're characterized mostly by the fact that they seem to have gone through some amount of differentiation. So remember, differentiation is when a body is like heated to melting, and then so the heavier parts of it sink inward, and then you get lighter parts, and then lighter parts, and lighter parts. So there are some asteroids that seem like they've gone through some form of differentiation, and they even have some like sort of volcanic plains, like you would see like on the ocean floor, or like on the smooth parts of the moon. Not only are there different ways we've classified them, but it seems like there's also a somewhat distinct sort of distribution of where these kinds of asteroids live in the solar system. This graph is particularly looking at the asteroids in the asteroid belt between Mars and Jupiter. So closer in seem to be more the S-type, right, the stony type of asteroids. As you get further out, the C-type tend to dominate. And metallic, I guess, is, again, they're pretty rare, I think, relative to the C and the S-type. These two probably make up like more than 90% of the asteroids we see, and metallic is maybe a couple percent, maybe, and the oddities are less than 1%, I would guess. Right, so the oddity things aren't even on this graph, but the metallic ones, like, there's a little bit, and they're actually seem to be peak kind of in between where the stony and the carbonaceous type. This is jumping ahead maybe a little bit, but what we see here is a piece of an asteroid that broke off of its asteroid parent at some point and eventually made its way to Earth. This is a really, really old rock, and we're pretty sure it's a piece of the asteroid Vesta, which is one of the largest asteroids. So it's a rock that fell from space. We call that a meteorite. And by dating, probably radiocarbon dating or radioactive dating of some kind, we determined that this rock is like 4.4 to 4.5 billion years old. So it formed in the very early solar system, giving us an indication that Vesta, its parent, where it came from, also formed in the very early solar system. And again, reiterating that these asteroids, most of them seem to have kind of been around and not changed much since the very beginning of the solar system, or since the very early stage of the solar system. So some things related to moons, when we're talking about asteroids, some asteroids actually have moons of their own. We would maybe call them more satellites than moons, but moon is a particular kind of satellite. The asteroid Ida has a much smaller asteroid that's actually gravitationally bound to it, so it's orbiting around it. Ida is about 56 kilometers, maybe 45 miles or so, and ductile, I don't know how to say those words, is about 1.5 kilometers across. And as I point out here, most asteroids, pretty much all asteroids, are some kind of grayish color. Right? These are color enhanced in a way, make it a little bit nicer for our eyes to look at. So some asteroids have moons. Some of the very large asteroids have kind of trapped or captured smaller ones that now orbit around them. So it's almost like a very small version of a planetary system, or a planet in a moon system. But then you kind of go up in scale, and some asteroids, it seems, have been captured by planets, and they are now moons of that planet, or satellites of that planet. So Mars actually has 2 moons, but they're very small, and as you can see, they're not particularly spherically shaped. Like the one on the left, Phobos, is a bit spherical, at least from that perspective. Deimos, I'm not sure how to say that either. Not very spherical, it's fairly small, sort of irregularly shaped overall, which partly what makes astronomers think that these are asteroids that were somehow captured by Mars at some point. Or maybe they were knocked out of their orbit in the asteroid belt and ended up, in orbit around Mars. And in fact, I think I mentioned last lecture, but a lot of the moons of like Jupiter and Saturn, they have tons of moons, and a lot of them seem like asteroids that are just captured at some point. One very interesting asteroid as of late is an object that was dubbed Oumuamua, something like that. Very interesting because it seems like the first confirmed interstellar object that we've seen, meaning that it originated outside of our solar system. The word Oumuamua means scout, or first to reach in Hawaiian. It's an interesting tidbit. The picture up here is an artist's interpretation. Again, asteroids are very small, they're hard to see, and this one is going very, very fast, and so we tried to get as good a look at it as we can, but the actual images that we have, nothing is that close for clear. From the observation we did make, it seemed like this object was actually really elongated, which is odd for asteroids, at least the ones that we see around here. Also seemed that it was metallic, or had a decent amount of metal, but also was rocky. Yeah, I think actually too they noticed that it seemed to be like toppling over as it went through the solar system. So it was like tumbling and zooming through. And being an interstellar object, it had this hyperbolic trajectory. You don't really need to worry too much about what hyperbolic means. You can see at least the shape of a hyperbolic trajectory by just watching the animated little image there. If you know what a parabola is, it looks kind of like a parabola, but it's actually even more sort of extreme form. So it comes in and gets like curved, or it's getting curved the whole time, but once it gets near the sun, it starts to really get pulled, and so it's bent, but it shoots off. I'm not sure how long it was actually in our solar system, but it wasn't all that long. Interesting stuff. As I mentioned earlier, there are plenty of asteroids that pass near Earth, right? A lot of small asteroids, like the smaller and smaller you get, the more and more asteroids generally there are. Some of them will actually impact Earth's atmosphere, and the majority of those are fairly small, and so they end up burning up in the atmosphere, and that's what we call a meteor, or often called a shooting star. Right? So you've seen plenty of little bits of asteroids that have impacted Earth's atmosphere. Generally, they don't do a whole lot. However, sometimes, if they're large enough, they can have substantial impacts, and in some cases, planetary scale impacts. Some examples that were in the book were an asteroid that fell, about 100 years ago in Tunguska, in Russia, and it was a piece of an asteroid that came into the atmosphere, and it was large enough that it made it pretty deep into the atmosphere before just sort of getting so hot that it combusted, blew up. Right, so it blew up above the surface, didn't make it to the surface, but it was a very powerful event. Right, you can see all the trees being felled. Luckily, there's not a lot of people around that area, so not a lot of people were harmed by that. Much more recently, in 2013, there was a pretty significant meteor that fell also in Russia. Russia's very big, so Chelyabinsk? I don't know, it's probably terrible. Anyway, this one was actually captured on video by a bunch of people, so you might have seen it. It happened almost 10 years ago now. So that's just a chunk of an asteroid, rocky stuff, that makes it pretty far into the atmosphere before just blowing up entirely. Like it's burning up as it goes, and then in the end, it sort of gets hot enough, and the atmosphere is getting thicker as you get further down, so it's like encountering more and more resistance as it goes deeper and deeper in the atmosphere until it's done. That one, I think, was less, I'm not sure actually. I know it blew out a bunch of windows in the area for like probably miles. I don't think anybody was seriously harmed from it, luckily though. However, the sort of extreme end of asteroid impacts are things you've probably heard of before, and there are signs left throughout the Earth of craters that asteroids have left when they made it all the way through the Earth's atmosphere and impacted the surface. And some of these can be very, very substantial. So for one, there is a very large crater left on the Yucatan Peninsula. I'm not even going to try to pronounce that. That's terrible. We think that asteroid that came in was about 10 kilometers across, right? About 6 miles across. And it landed about 65 million years ago, which has led a lot of people to believe, and there's kind of the generally accepted theory, that that impact was sort of the beginning of the end of the dinosaurs, the era of the dinosaurs on planet Earth, along with many other species at the time. It wasn't necessarily that asteroid impact itself directly killed a bunch of dinosaurs, but an impact of that size can throw up a ton of debris into the atmosphere, like dust and smoke and such that you actually cover the Earth in this layer of just dense material enough that you block out the sun pretty much almost entirely, right? And if you don't have the sun, then plants are going to die. Then the things that eat the plants are going to die. Then the things that eat the plants are going to die. So this event sort of started a chain reaction that led to the downfall of a bunch of species over time. Sort of lucky for us, because we probably wouldn't have made it past any other evolutionary hurdles if there were still so many big things around. Interestingly enough, it's thought that there was actually a second impact right around that time too, and the thinking is that this might have actually been a larger asteroid overall that broke up before it actually hit Earth, and so one of them hit right here in the Yucatan Peninsula, the other one hit the south of Africa somewhere. Moving on to comets then. Comets, as opposed to asteroids, are not mostly rock or silicate, they're mostly ice, with a little bit of silicates. So one way of describing a comet is they're like a dirty snowball. The book says the average size of a comet we've seen, or the ones we've seen, about 1 kilometer. I'm not even sure if or what the largest comets would be, but I'm almost positive that they're much smaller than the largest of the asteroids, right? Because the largest asteroid was almost 1,000 kilometers. We have a table of some of the more famous comets. Probably should have tried to put Neowise in there, but I did not. So another thing about comets is they generally have very elliptical orbits. Like in the picture down the left there, part of their orbit is rather close to the sun, but most of the time that the comet is orbiting, or the comet's moving around in its orbit, it's pretty far away from the sun. So in one way of thinking about comets, when we classify comets, is in their period, which is just, how long the whole trip takes to go around. And you sort of have like a long period comet and then short period. And so long period comets are like ones that take like 1,000 or thousands of years to make their full orbit. On the shorter end, the short period, we actually have some of those years written down, like even 100 years or so is still considered short. Halley, the comet Halley you might have heard of. It's a fairly famous comet that comes around in this sort of 76-ish year period. And it was one of the comets that sort of gave us a lot of early information about comets overall and the fact that they are periodic. And then probably one of the first to be explored by spacecraft in the late 80s. And then you get down all the way to some rather short periods of a few years. Some of these comets, shortest known period, about 3 years, a little over 3 years. So one of the things about comets is not all of them have this orbit that brings them pretty close to the sun, right? There are plenty of comets that are just happily orbiting around outside of Neptune, right? In that sort of deep freeze of the solar system. Yeah, so there's plenty of those. There are some, though, like these ones listed here, whose orbits bring them close to the sun. And when they get close to the sun, the fact that they're mostly made out of ice means that they get heated up and that material starts to vaporize once it gets nearer to the sun. So that's why when people think of comets, you often think of like this bright ball thing with these long tails coming off the back. And so that tail is like the vaporized material that's coming off of the comet. We have the picture down there on the left of a comet sort of like moving in and it's going around in this direction, and the comet's tail really only starts to form when it's near to the sun. When it's over here, it's just like a chunk of like ice and a little bit of rock, that dirty snowball kind of thing. All right, it's not being vaporized. And technically there's two different sort of main portions of the tail, but we'll talk about that more in a minute. Yeah, and as you might notice, the tails don't actually align that much with the direction the comet's moving. The tails have a lot more to do with the direction towards the sun from the comet. It's actually the sun that's vaporizing that stuff and sort of pushing it away from the comet. And it's pushing it away from the sun. And then there's this little animation of some comets, and I think shows like that tail actually forming and always kind of pointing away from the sun, and then as it gets further away from the sun again, that tail goes away and keep going. So looking a little bit closer at the comet Halley, that image on the left was taken by a telescope in Chile, so the ground-based telescope, done in '86. The image on the right here, I don't have it written here, but I'm pretty sure that's taken by a spacecraft. Like to get that detail of the nucleus of the comet, seems like you probably have to be out in space and probably close to it. Yeah, so in the close-up you can see that it's not just this like fuzzy ball. It's actually like a kind of gnarly looking hunk of stuff, and that stuff is mostly ice. And again, remember ice, not just like water ice, but ammonia, methane, other things like that. Halley was a fairly large comet, I think, its nucleus being about 10 kilometers. And in this picture too, you can kind of see like that fuzz around sort of the nucleus of the comet. That's some of that ice being vaporized. And you get even further away, you don't really see the nucleus anymore, just kind of see this fuzz in the tail as well. As I said, Halley's comet, or the comet Halley, comes around about every 75 years. And supposedly, there are like documented recordings of its passing every 75 years, roughly, for something like 2,200 years now, back to like 200 something BC. So people have been looking at this comet passing by for quite a while now. It's a pretty spectacular sight. Right, so a little bit more detail about the pieces of the comet, but not just the comet, right? Because the comet itself is really just the nucleus, right? It's really that hunk of ice and a little bit of rock. The thing that we usually think about when we say comet is a comet that's vaporizing, or it's parts of it are vaporizing because it's getting close to the sun. Right? So keep in mind that that's a kind of extra, like you don't really need that tail in order for it to be a comet. That's a particular part of the lifetime of a comet, if it does approach the sun. So that said, if you think about the comet on its approach, it gets near the sun, and within 3 or 4 AU, so right, about 3 or 4 times the distance the Earth is to the sun, within about 3 or 4 times that, then comets will start to warm up enough where that vaporization will start happening. Ices will start to get turned into gas and they'll be expelled from the nucleus of the comet. The diagram there shows a number of the different pieces, right? I've already been mentioning the nucleus is what we call sort of like the main body of the comet, that ice and that rock. When it's being vaporized, or parts of it are, then you form all these other pieces, the coma, just like a kind of like atmosphere almost that forms around it. There's actually 2 tails. One is the dust tail. You can see that better maybe in this picture down here. The dust tail is kind of maybe the most iconic thing you would think of when you see a comet, or think of a comet. But there's also a gas tail. So dust tail is like dust. It's pretty small stuff, but the gas one is like single atoms and molecules, right? So very, very small stuff. And so the dust tail being like made of slightly larger stuff, it's pushed away from the sun, right? Like in the picture down here, that's the direction coming from the sun. In the diagram up top, G is the direction of the sun, and the tails are getting pushed back the other direction. The dust tail gets pushed back, but the stuff that it's made up is a little bit larger, and so it ends up sort of dragging a little bit, or it sort of like curves a little bit along the direction the comet was going. Right, so the comet's going that way. In this picture down here, the dust tail ends up getting kind of curved a little bit that way. They're still mostly pointing away from the sun. The gas tail, though, being so much lighter, really the solar winds that are pushing the gas tail in this direction. And it's so light that the solar wind is completely dominating the direction that gas tail ends up being. So when you look at the gas tail, you can draw a line along that tail, and it's going to point towards the sun. Besides that, there's this sort of envelope of hydrogen, so just hydrogen gas that forms around outside of the coma, which can be quite large. But something that we'll come back to in a little bit is that when these comets go by the sun and they leave this dust tail, right, that dust tail, there's nowhere that it's going to go. So the tails of comets end up sort of hanging around in the solar system. They kind of continue along, orbiting like anything else would in the solar system. And then occasionally the Earth passes through those tails, sort of the remnants of the comet that went through, and that's what leads to meteor showers. But I'm getting ahead of myself. Last thing, particularly about comets, is one comet that we have visited, we sent a spacecraft to, and landed on. Pretty interesting stuff. This was not all that long ago, maybe 2015, 2016? Yeah, I think about 2015 somewhere where we actually landed. So at first this spacecraft kind of got into the same orbit with this comet, and the comet is 67P. It has a longer name, or longer designation that's named after the people that spotted it first. I don't recall their names though. Anyway, sent this spacecraft to kind of meet up with the comet's orbit and so it sort of photographed it from nearby for a little bit, and then eventually sent off a smaller spacecraft to land on. And the images on the top, of interest at least, is that in very short periods of time, it seems like some of these sort of streams or like jets of vaporized gas can form. So between picture A and B is only a few minutes. When you think about a comet or parts of a comet vaporizing it as it comes towards the sun, it's not happening everywhere all at once on the comet. It generally seems to be pretty localized and will kind of start and stop in different places pretty quickly. So that image there is like on the far left, there was nothing happening, and then a couple minutes later, it's like sort of a stream of that vapor comes up. Image here, just a further out picture of this comet, pretty oddly shaped thing. It's not particularly large, so it doesn't really tend to form into a nice spherical shape. So there's actually sort of multiple jets of vapor coming off of the comet when you look at the large scale. This down here is just a really cool image of the surface. Right after the craft landed on the surface, it took some images. I think the story is that it fell into a shadow for a little while, and it only had solar panels, so it kind of went dark for a little bit until the comet revolved around enough where the sun ended up hitting the lander again and its batteries could charge up, and it was able to take some images and send some information back. So we got these very cool, sort of eerie images of the surface of this comet. So it looks pretty alien in some ways, like very different, or it seems kind of eerie and odd, but I don't know. I look at it, and it also seems like, maybe that could be somewhere in the depths of Siberia or in Antarctica. Sort of like alien, but also somewhat familiar. It's very strange. I mentioned that there are other things besides all the stuff we talked about so far, planets and moons, asteroids, comets. The more we look, the more we find other things that don't quite fit into the categories maybe that we have already. So things aren't so clean cut, as I've pointed out on multiple occasions. For one, there are objects that seem to share some characteristics of asteroids and comets, and they also, I guess, generally have orbits somewhere in between Jupiter and Neptune. We've termed them centaurs, half man, half horse. Like half asteroid, half comet, something like that. The diagram here is just showing the orbits of some of the planets, and then also one of these centaurs, Chiron, kind of an odd orbit, at least compared to the planets. Besides the centaurs, there's other things which we end up terming Trojans. I'm not terribly familiar with them, so to say that they're these smaller sort of objects, but they actually share the orbits of much larger bodies, like a planet. In particular, the animation there is showing two of these known clusters of Trojans that share the orbit of Jupiter. One of the clusters you can see is kind of in front of Jupiter in its orbit, the other one's sort of behind Jupiter in its orbit. So like most things we'll talk about, it's not so clean cut as, well, maybe you didn't think it was clean cut already, but it's even less so. The universe is a dynamic and often messy place. So, and one more thing before talking about meteors and meteorites is things we just kind of broadly term trans-Neptunian objects, or TNOs, literally meaning past Neptune, beyond Neptune objects. Right? So in our solar system, we got the sun, we got all the planets, Mercury, Jupiter, Saturn, and Neptune is the furthest out of the planets. Anything past Neptune is broadly dubbed trans-Neptunian objects. And that includes dwarf planets like Eros and Pluto, which in some senses can seem like very large asteroids, right? It's kind of like a gray area. And then beyond that, like I mentioned, there's this sort of theorized cloud of icy debris, but this hasn't really been, would you say, observed as of yet, so it's still kind of a theoretical thing. And if it's there, it is an incredibly large thing relative to the size of the solar system. If you look at this axis in the image, where we're going from the sun all the way out to Neptune and the Oort cloud, the axis there is what we call a logarithmic axis. So it goes 1 is the first big mark, that's the first distance, 1 AU. The next mark is 10. So each tick is 10 times as large as the last one. So Saturn is about 10 AU. You go 10 times that, 100 AU. We're out sort of at one of the boundaries of the solar system that we think there is the heliopause, or the outside, the heliosphere. That's apparently roughly where Voyager 1 is, or at least was a couple of years ago. We sent out Voyager in like the 80s or maybe the 70s or something, and it's still going. Voyager 2 as well, I think. And they've been going for decades, and they're kind of still in our solar system. You know, depending on how you classify the edge of the solar system, they're still around. But then the Oort cloud could go from something like 2,000 AU out to like 200,000 AU. Just this massive, massive region around the solar system, right? And it's not like the asteroid belts where it's like almost this sort of like plane or like ring going around the sun. It's thought of to be like a sphere that actually encompasses the whole solar system. And finally on this chart is somewhere in between 100,000 and a million AU is our nearest stellar neighbor, Alpha Centauri. Or one of the nearest. I think there's Alpha Proxima. I always get it confused. But Alpha Centauri is, if not the nearest star, it's definitely one of the very near stars to us. And one other interesting thing to point out is that if this Oort cloud is actually a thing, then it's thought to be made up of like trillions of objects, and the mass of all those objects put together would actually be very significant in terms of the mass of the total solar system, or the total mass in the solar system. So think back a while ago when we looked at the mass distribution of the solar system, it has to be adjusted if this turns out to be a thing, or turns out to be the way that we think it is at least. So the last things we'll talk about in this lecture are generally like pieces of asteroids or comets that encounter Earth, right? Hit Earth's atmosphere. Some of them make it through, some don't make it through. The image here is showing a regular meteor or a shooting star over the ALMA telescope array. I think that's in Atacama in Chile. What's very nice about meteors and meteorites in particular is they're sort of samples of the early solar system. So remember I said a lot of the comets and asteroids seem to have not really changed much since the formation of our solar system. It's sort of been stuck in this deep freeze since then. So it can be very nice when some of them encounter Earth and they sort of just come our way. It's like a delivery from the early solar system. We don't even have to go and do anything for it, right? It comes to us. Especially meteorites that actually land on the surface give us things to look at and examine in great detail. So when we think about meteors, they're kind of broad classes or ways to categorize meteors. One way is to think about the sort of different origins of them. And thinking about it that way, they sort of break down into what we call sporadic meteors and meteor showers. So sporadic meteors is just like a normal shooting star that you see. They happen quite regularly. If you're in a really dark area on the Earth and we're looking up, paying attention, you could see just a normal amount of shooting stars or amount of meteors, something like 6 per hour. The average size of these sporadic meteors is like the size of a pea, like a gram, though there can be larger and larger, and once they get to the size of like a bowling ball, then they start to have a chance of actually making it through the atmosphere and hitting Earth's surface. And that's when they become something we call a meteorite, or that's when we start calling them meteorites. It's pretty incredible though that even the ones that are like the size of a pea, this little tiny gram of space stuff, it is moving so fast that when it hits the Earth's atmosphere, or when it starts to go into the Earth's atmosphere, it hits with the energy of like a large artillery shell. Give you some idea of energy related to just the motion of something, right? If something going really fast, it's got a lot of energy. So besides the sporadic meteors, sort of normal, day to day, we also have meteor showers. And those, it can be anywhere from like a dozen-ish per hour to like 100 per hour. Or if you get meteor showers that are like very high rates, that's up to like 1,000 or over 1,000 meteors per hour. And that's, I think, where we start going from saying shower to a storm, meteor storm. Not very common. Meteor showers do happen fairly often though. And as it turns out, the showers are occurring because that's a place where the Earth is passing through the tail of some comet. So if you recall, I said that when comets are going near the sun, they're letting off some of this gas and dust, and that dust ends up sort of hanging around and still orbiting around the sun. So every once in a while, the Earth passes through those kind of remnants of the comet's dust tail, and as we do that, there's a bunch of dust and stuff in there, and that is how we get meteor showers. And just to be clear, that the origin of these things is very different. The sporadic meteors are just kind of random debris from all over the place in the solar system. Meteor showers are remnants of comets' tails that we pass through the Earth. So here we have pictures of a standard meteor. Down here is something more like a meteor shower. I'm sure this is like a time lapse, or even a composite image. But if you ever see a very high rate meteor shower, it's quite a show. A bit more about meteor showers then, and why they seem to emanate from a particular spot. Well, hopefully it makes sense now, is because we're running through the tail of this comet, or the remnants of the tail of a comet that passed at some point. So here's like the tail, and the Earth is going towards that tail and pushes through it. Then all of those meteors are sort of looking like they're coming out of that single sort of area of the sky where our atmosphere is impacting the comet tail. So the source, or like the place where all those meteors are kind of coming from, is what I guess you call a radiant. So the image on the left is showing, roughly what you might see when you look for a meteor shower, or like the kind of pattern of meteors that you see when you watch a meteor shower. And on the right here, I just showed an image, hopefully to make it clear why it should make sense that if a lot of things are originating from a particular area and coming at you, that you'd end up seeing them all as these lines moving away from that area. It's very much having to do with like a perspective. So if you think about the lines in a hallway, they might all be straight and parallel to each other, but from our perspective, they actually all seem to vanish or move towards a single point, or emanate from that point. You can think about it that way. Meteor showers are generally named after an area of the sky or a constellation where they originate from. So that's why we have like the Perseid meteor shower, the Leonids, Geminids. And there's this international meteor organization that you can check out if you're interested in seeing like when's the next meteor shower. Not all meteor showers are created equal, so if you're going to look up when one is and you want to see a really nice show, then it might be a while before you actually are able to see a really high rate meteor shower, or even a meteor storm. Meteor showers, they happen pretty regularly. There's these tails of comets that are just kind of lingering and orbiting around the solar system, and the Earth passes through them periodically. But it's not like those tails are just evenly distributed debris and dust. As I showed you earlier, when we were looking at the comet up close that the Rosetta mission observed and got close to and landed on, we saw that it wasn't the case that the comet was just like vaporizing continuously, a sort of smooth, even pattern, right? That would result in a nice even tail. All of our meteor showers would look fairly similar. Right? But that's not the case. Right? We saw that there were like jets of this vaporized gas that would maybe stop here and start off over here and stop here. Right? So it's like unevenly distributed dust in this tail, which means that at some places, when we go through that dust tail, it's a lot more dense. There's a lot more dust. We're going to see a lot more meteors in that meteor shower. Some places it's a lot less. You don't see quite as many. One of the most recent, just sort of epic meteor showers was the Leonid shower of 2001, and that was about 8,000 meteors per hour. I'm pretty sure I watched that. It's like I have this memory from when I was a kid of waking up in the middle of the night when I was at this like camp thing, going out and watching this meteor shower. And for the longest time, I thought it was just like my memory had been enhanced, like I had kind of exaggerated it a bit. But I just remember like tons of meteors going constantly. So maybe I hadn't exaggerated that much, because I'm pretty sure that was the shower that I saw. However, Leonids this year probably only going to be like 10 or 15 meteors per hour. So not nearly as spectacular. So the material that actually makes up these meteors, right, being from a comet's tail, is very light material, not very dense, less than a gram per cubic centimeter. If you were to have like a chunk of this material and you put it on a table, it would just collapse under its own weight. It's a very light or like fluffy material, which is also why meteor showers, none of that stuff actually makes it to the ground. Right? That's all little dust from comets' tails, way too light and insubstantial to actually make it through our atmosphere. Let's talk a little bit now about the kind of stuff that does make it through our atmosphere. Right? I've mentioned this a number of times, but just to reiterate, when random debris, some of that like more sporadic meteors, when they impact the Earth's atmosphere, turn them a meteor, and some of those are large enough and substantial enough to actually make it through the atmosphere and hit the ground. That's a meteorite now. So what are the kinds of meteorites, or how do we classify meteorites? I should say it's complicated. There are multiple ways of classifying meteorites, different ways that people come up with. These are two of the main ones, two of the ones that the book presents, so we'll talk about those. So one way of classifying them is by like the kind of material they're made of. And that classification breaks down into the irons, iron meteorites, iron being a metal, and those meteorites are mostly made of metals, particularly like nickel and iron. Besides the irons, you have the stones, or stony meteorites. As the name again sounds, it's mostly rock, silicates. And then finally, there's like the mixture of the two, the stony irons. Those, however, apparently are quite rare in terms of meteorites. Alright, so that's one way of classifying, is like by the kind of stuff they are, the material. Another way of classifying them is by differentiation. Basically, whether they've gone through a process of differentiation at some point, or whether they came from a larger object that had differentiated. So in that classification, we have like the primitive objects, and those are the ones that don't seem to have ever gone through any differentiation. So these primitive ones are the oldest objects pretty much that we've ever found, or that we have found so far. So they haven't really been heated since basically the beginning of the solar system. Or maybe they were never heated, they're just clumped together. For the most part, the primitive meteorites seem to be fragments from asteroids. That's what we've found. The other end of that then are the meteorites that are differentiated, or they seem like they've at least gone through some kind of differentiation since their formation. And a lot of these seem to be fragments from larger objects that had gone through differentiation, right? Because most of these meteorites are not large enough that they will likely differentiated just by themselves, right? They probably wouldn't have been impacted enough and gather enough heat to actually melt and do that differentiation process. So it really seems that these ones are just parts of objects, larger objects that did go through that process. Things like protoplanets. And like I said, meteorites are pretty much the oldest things that we've managed to date in our solar system. The oldest are something like 4.5 to 4.56 billion years old. And in fact, the dating of the oldest meteorites is sort of like a benchmark that we use to date the solar system. Another way of saying that is like when the first things solidified in our solar system. And really to hammer away the point that the naming convention is not very great here, right? Like I said earlier, in astronomy, there's a number of places where, we still use the same name for things, even though we know that they're not really the same things anymore. It's just unfortunate. But when we talk about meteorites, they do not come from meteor showers. It sucks. It's just what it is, right? So meteors are, again, typically comet fragments, or maybe very small asteroid fragments, and they burn up in the atmosphere. Meteorites are pretty much all asteroid fragments that are large enough, heavy enough, and dense enough to make it through the atmosphere. Remember, meteor showers are specifically comet tail dust. None of that ever makes it through the atmosphere. So we'll just end by looking at a few images of meteorites. So in the upper left there, A is a stony meteorite. Also falls into a primitive category, meaning it's hasn't gone through any differentiation process. Yeah, very, very old. It also says it's carbonaceous, meaning it has a decent amount of carbon, makes it kind of dark. The middle one is an iron-type meteorite. I'm not sure if it's specifically iron, but it's probably at least substantially iron and nickel. And that is part of a larger meteorite, I guess, that formed what we call the meteor crater in Arizona. If you've ever seen that, it's a cool landmark. And finally on the top, in C, this is a stony iron meteorite. Again, quite rare among meteorites, but very pretty to look at. On the bottom left then is a picture of some scientists that are looking for meteorites in Antarctica. So meteorites, just like sporadic meteors in general, they just kind of happen every once in a while. It's not that terribly uncommon for meteorites to land, right? For a meteor to go through the atmosphere and hit the Earth's surface. It happens fairly regularly. Most of them are not that large still, so you almost don't even notice it unless you're rather close to that event. But the thing is, over the course of Earth's history, we've had a lot of meteorites that have hit. If they land in places that are like active geologically, then it's really hard to tell that they are meteorites, because some processes will happen where it might get covered up by something else. It might get broken down by some kind of erosion. So a lot of meteorites that have landed, we're never really going to tell if they're meteorites unless you go and scour every rock and look at its isotopic readout and such. However, in places like Antarctica, there's very little activity that's happening, geologically speaking, right? For the most part, if something goes and drops, it just kind of frozen over and sort of like a freezer out there. It just kept that way for a long, long time. So one of the places that scientists have found to look for meteorites and to be able to gather substantial amounts of meteorites is in Antarctica. And then the very last picture here is of a particularly interesting meteorite, the Murchison meteorite, named after the town the town in Australia that it fell. Particularly interesting because it was found that this meteorite contained amino acids. Amino acids are some of the building blocks of life as we understand life, at least. Beyond that, even, the amino acids that were found in this meteorite apparently were rather odd in that the amino acids that formed and evolved, or that we have on Earth, have a sort of handedness to them. The structure of the amino acid is such that it kind of curls or curves in a direction, particularly a left-handed direction. In this meteorite, we found amino acids that had that left-handed direction to them, but they also found ones that had the right-handed direction to them, which we don't have on Earth. They're not around. It was a very interesting kind of thing where this meteorite contained stuff that's very helpful in building life as we know it, but it contained pieces that we don't have around here. Yeah, kind of wild stuff. Which is partly what leads people to think that it may have been the case that life on Earth was at least partly seeded by meteorites falling. And so at some point a long time ago in the Earth's past, we had meteorites impacting that had amino acids and had some of these other necessary or things that make the building of life possible on them, and they were deposited on Earth from these outer space objects. That is all I got for this lecture, so I hope it was interesting and made sense, and we'll try some more stuff later. See you.